the force is proportional to the to the displacement of the particle. Actually, my spring is somehow very ideal, so the force is 0 if the 2 points coincide. Okay, and well, if you give it a little speed in this direction, it's going to move on an ellipse, right? As long as this center is fixed. But then, well, what I'm looking at is the case where you actually move around the center. So this somehow corresponds to an earthquake, right? And here you can see what happens then. So I prepared this little animation. Here it is. So the red point is the particle. It's moving around the anchor. And the earthquake starts now. So the anchor moves around. The particle is somehow well, it's moved around a lot, and in the end, when the earthquake is over, it moves on a completely different ellipse. Okay, so that's what's happening in the generic situation. Now, if by some miracle, well, if the particle moves on a certain ellipse, and after the earthquake, it moves exactly on the same ellipse, I would call this a miracle. Okay, so here you can see such a miracle. Okay, the particle, you should try to memorize the ellipse. Okay? So it's moving on this ellipse, now the earthquake starts, so the particle is somehow shaken around a lot, but when the earthquake is over, which is in 2 seconds now, okay, it's back on the same ellipse. Okay. Now, as a matter of fact, this miracle does not come alone. There's another miracle. The problem is that the other miracle looks very similarly because it's actually the same ellipse, but the earthquake starts when the particle is at a different point. Okay, so here it is. Oh. Okay, it's the same ellipse, and the earthquake starts when the particle is more here. Okay, this is the earthquake, and well, the particle is moved around a lot, but when the earthquake is over, the particle is back on the same ellipse. Now you might not believe that these were two different miracles. So here's the proof. So this is the first miracle. Okay, the earthquake starts when the particle is there. Oh, I have this. So here the earthquake started, and you can see how the particle is moved around, but in the end it's back on the same ellipse as before. And soon you can see the second miracle. So this is again the particle moving on the same ellipse. And after 2 rounds, the earthquake starts. So you can see that the earthquake is the same, right? It traces out the same path. And when it's over, the particle is back on the ellipse. And here you can really see that we have 2 different situations, 2 different paths. Okay. Now, this comes with some theory. So let me maybe explain this a bit. So a corollary to my main result says that if the earthquake is not too strong, in fact, at least 2 miracles happen. So I'm going to explain this later a bit. And for this, let me introduce some framework. So I look at the symplectic manifold, omega. For example, you can take the standard symplectic form on R2n. It's given by this formula here. It's the sum over those wedge products, dqi, and so on. If you take n equals 1, this is really the standard area form in R2. And the coordinates are labeled here with qi, q1, p1, and so on. Okay. Now I take a coisotropic submanifold. So by definition, this means that it's a submanifold where at each point in the submanifold, the symplectic complement to the tangent space is contained in the tangent space itself. And the symplectic complement is defined in this way. It's all vectors in the tangent space to the whole manifold, which annihilate vectors, all vectors which lie in the tangent space to F. So we want this subspace of the full tangent space to lie inside the tangent space to N. Then we call it submanifold coisotropic. For example, whenever you take a real hypersurface of a symplectic manifold, it's automatically coisotropic. And this is a very interesting example. It's the one which applies to the situation here, as I'm going to say in a minute. Then we also fix a map from M to N. Now we can define what we mean by a leafwise fixed point. So by definition, this is a point in the Coisotropic submanifold, which is mapped under phi to the leaf through this point, through itself. So let me draw a picture here. So we have our Coisotropic submanifold. We might have some topology. And here we have a point x. And the leaf through this point is by definition all points in N, this is N, which we can reach through paths which are tangent to the isotropic distribution. So the isotropic distribution is by definition the distribution on N given by the symplectic complement to, well, the tangent space to N at each point, right? You can do this at each point and you get a distribution, and it happens that it is integrable because the form omega is closed, the assumption, and then you get a foliation, and the leaves of these foliations are called the isotropic leaves. Now, leafwise fixed point is a point in the manifold N, so that under the map phi, we end up on the same leaf, right? So it can be very far from X, but it has to lie in the same leaf. Any question about this? Now, in our example of the earthquake, we take as our symplectic manifold R4 with the standard structure, and we take the sphere of radius r for some r as our Coisotropic submanifold. Now, and phi is the time evolution for the earthquake. So this sphere corresponds to a level set for the Hamiltonian function, which generates the movement of this particle. So under some normalization, this Hamiltonian is given by h of qp equals the norm of p squared over 2 plus the norm of q squared over 2. So this is kinetic energy and this is the potential. And the movement of a Hamiltonian system is described by Hamilton's equations using the energy. And the leaves through points in this sphere are exactly the orbits, trajectories, under the unperturbed system. Okay? So we take phi to be the time evolution of the earthquake, which means we take the time-dependent Hamilton function, which corresponds to the potential which you get when you move around the center. Okay? So it's time-dependent. And we take its time 1 evolution, and a leafwise fixed point is then exactly a point which, after time 1, comes basically back to the initial state except for a phase shift. Right? That's what it means to lie on the same leaf. Okay, so that's what we call a miracle, right? When you come back to the same ellipse and you go the same way, in the same direction. So the leafwise fixed points are exactly the miracles. Now, as I already said, phi has a special property here. It's a Hamiltonian diffeomorphism. So let me describe what that means a bit more concretely. So whenever you have a smooth function on the manifold M, then you can define a vector field xh via this equation here. So here you use that the form omega is by definition non-degenerate. So there exists a unique such vector field, and the Hamiltonian diffeomorphisms are defined to be all diffeomorphisms of the manifold M, which you obtain by taking a time-dependent Hamiltonian function and then defining the vector field here, which then will depend on time, and then use its flow, time 1 flow. Okay. Right. Any question about this? So these are the basic objects which you want to consider in symplectic geometry when you do dynamics. Okay. So physical systems have time-dependent physical systems are described by Hamiltonian diffeomorphisms, and they have one nice property, namely the pullback. Well, they leave the form omega invariant. Okay, they're in particular they're symplectomorphisms. Now in the sequel, I'm always going to assume that my map phi is actually Hamiltonian diffeomorphism, and then we can ask the following question, namely if phi is not too far from the identity in a certain sense. What lower bound is there on the number of leafwise fixed points, i.e. on the number of miracles, if you want? So this question is a famous, or maybe one of the well-studied question in two extreme cases. So in the first case, the Coisotropic submanifold is the full manifold, and then this is really a fixed point in the original sense. And the question one particular formulation of it is called the Arnold conjecture. So there you conjecture that the number of leafwise fixed points is bounded below by the sum of the Betti numbers of the manifold. This is the homological version of it, and this has been proved. There's another version which is still open. And in the other extreme case, the dimension of n is half the dimension of the manifold. And then a leafwise fixed point is really an intersection point of the submanifold n and phi inverse of n. So in the simplest case, when you take a circle in R2, this is really in R2. So this would be n, and this would be phi inverse of n. So the circle is somehow moved, but it need not look like a circle anymore. And a leafwise intersection point is really an intersection point of these two circles. Okay. Now, in this particular case, when n has half the dimension of the manifold, then the n is called Lagrangian. And this is a very well-studied problem in this case. But the intermediate case has not been studied that much. It has caught attention only recently. There has been a lot of activity recently. And my main theorem here gives some answer to this question. So it says the following. So assume that the symplectic manifold is geometrically bounded and that the coisotropic submanifold is closed and regular. Then there exists a positive constant so that whenever you have a Hamiltonian diffeomorphism who is closer to the identity than C in the Hofer sense, then the number of leafwise fixed points is bigger than or equal to the sum of the Z2 Betti numbers of n. And also you can choose this constant bigger than or equal to the minimal symplectic area. Now maybe I should explain some of these words here. I'm not going to say something about everything, but so first of all, geometrically bounded is a mild condition of the manifold. For example, any closed manifold has this property. Also R2n has this property with the standard form. And whenever you take a product of two geometrically bounded manifolds, it's again geometrically bounded. Now, the Hofer distance here is also it's a distance function on the group of Hamiltonian diffeomorphisms, and it's a very weak map, so it's very small. For example, it allows, if you can have small Hofer distance and still move any finite number of points as far as you wish. Okay. Furthermore, the minimal symplectic area is defined to be the infimum over the integrals u star omega from over all maps from the disk u. I mean, the map is called u from the disk to m, which maps the boundary to one of the leaves. So you have a disk like this. So here is my leaf, and I have a map from the disk. So it should somehow close. The leaf should be closed. Okay. And then you can have a map from the disk which has boundary on this leaf. So that's what I'm looking at here. And then you take integrals on u star omega, or use such a map, and you do the infimum over all such maps, and only over those for which this integral is positive, and that's the minimum symplectic area. So we will see what this is in an example. Right. Let me also mention that regular means that the coisotropic submanifold admits a symplectic quotient. So, for example, the sphere, which we just had before, has this property. The quotient is Cp n-1. Now, the proof of this theorem is based on a certain Lagrangian embedding of n and work by Yuri Chekhanov. Right. Let me mention something here, namely, this bound which I give here is optimal if there exists a Z2 perfect Morse function on the manifold n. And here's a concrete example. So we look at the Stiefel manifold inside the K by n complex matrices. So by definition, these are the orthogonal K-frames, K by n matrices with orthogonal rows. And they're all normalized, the rows. And under these assumptions, well, in this situation, the hypothesis of the theorem actually satisfied. And the sum of the Betti numbers is 2 to the k, and the minimal symplectic area is pi. So whenever the theorem now states that whenever you have a Hamiltonian diffeomorphism whose Hofer distance to the identity is less than pi, then there are at least 2 to the k leafwise fixed points if the pair n phi is non-degenerate in a certain sense. So in the case where you have a Lagrangian non-degeneracy, it means exactly that the two Lagrangians n and phi inverse of n intersect in a transverse way. And in this case of a fixed point when you have n equals m. It's a non-degeneracy condition on the differential at each fixed point. It's not allowed to have an eigenvalue of 1. Yes, question.
So is a set fixed Vn always a discrete set?
It's discrete if under the assumption that that n phi is non-degenerate.
Okay.
Otherwise, it's not. As you can see when you take the identity. And thank you for the question.
Are the orbits always closed?
Yes, that's a consequence of regularity here. Now, let me mention here that for k equals 1, Hofer proved that there exists at least one leafwise fixed point if the Hofer distance is less than or equal to pi. So this is an improvement. Well, if the pair n phi is non-degenerate. And then let me also mention that for k equals 1, Peter Albers and Urs Frauenfelder recently proved that the same bound as I, so they have at least two leafwise fixed points if the Rabinowitz-Floer function is Morse. Okay. Now, let me say something more about similar results here. So, the question of leafwise fixed points was first considered by Moser in 1978 or so, and he proved lower bounds on the number of leafwise fixed points for C1 close diffeomorphisms, Hamiltonian diffeomorphisms. So they were C1 close to the identity, which is a much stronger condition than having Hofer closeness. And Banyaga improved the results by Moser, still using C1 closeness. Now, Hofer and Ekeland were the first ones to look at a more global situation. So they have a condition involving the Hofer distance, and all the subsequent people also have the same condition, including me. Not the same condition, but always a condition involving the Hofer distance. So Ekeland and Hofer looked at the case of a hypersurface in R2n of restricted contact type. And then Dragnev extended this to general codimension, and Victor-Ginsburg generalized in another direction. So he looked at subcritical Stein manifolds, in particular R2n would be such a case, such an example. And he looked again at hypersurfaces of restricted contact type, and Bajak-Gurel extended this to general codimension again. And then Peter Albers and Urs Frauenfelder proved that you actually have, so in all these results where you have a global bound on the distance, I mean you have some bound on the, you assume that the Hamiltonian diffeomorphism is close in the Hofer sense with the identity. In all these examples they only prove that there exists at least one leafwise fixed point. Okay, but then Peter Albers and Urs Frauenfelder, they actually proved that there exists infinitely many such leafwise fixed points for the unique cotangent bundle in the cotangent bundle to a closed manifold which has finite pi1. And Jung-So Kang, he recently proved a similar result. Let me maybe emphasize here that, as to my knowledge, if you look at a case where the Coisotropic submanifold has more than half the dimension of m, and it has at most the dimension of m minus 2, then, and you don't assume C1 closeness of phi to the identity, then I think that my result is the first one where it says more than one leafwise fixed point. Okay. Any question?
Before you go on, let me make sure that I understand. So the first example when you show the earthquake, you have two miracles.
Yeah.
So that each miracle corresponds to the fixed point? Or?
Yes, yes. Each miracle is a leafwise fixed point. You can think of it this way. At the point when the earthquake starts, your particle has a certain position and a certain momentum. And this is exactly the coordinates QP in R2n, here in R6. And, well, under the map phi, they are mapped to the Hopf fiber through the same point. That's what it means to be on the same ellipse, right? Because you have automatically the same speed, but you could go the other way, actually. Right? So these are exactly the fixed points. You can do the same in any dimension. Yeah. The same applies in any dimension. Any other question? So, by the way, what about the time? Is there any clocking?
You have 25 minutes.
Oh, that sounds good. Yeah. Now, I would like to talk about some application. This is a presymplectic non-embedding result. So let me tell you what I understand by a presymplectic form. So this is a two-form on a manifold which is closed and has constant co-rank. So here the co-rank is the dimension of the map which takes an element of, which takes a vector in the tangent space and gives you, plugs it in as first argument into omega. Okay, so you get a vector in the cotangent space. And if the form is symplectic, this means exactly that this kernel is 0, so the dimension is 0. And the other extreme case is where the form is actually the 0 form, and then the dimension of the kernel is the full dimension of M. Okay. Now, when you have two such presymplectic manifolds, then you can ask whether one of them admits an embedding into the other one so that the second form is pulled back to the first form. So this question has been studied a lot in two extreme cases, namely when the two manifolds are actually symplectic and of the same dimension, then this is the symplectic embedding problem, and it gives rise to the notion of a symplectic capacity, for example. And the other extreme case is where the second manifold is still symplectic, but the first one has actually the 0 form and it is half-dimensional. And then this is exactly the Lagrangian embedding problem. So this has been studied a lot in symplectic geometry. And the more general case, I don't know any reference for it. If you know, please tell me. So I think that it's largely unexplored, the general case.
So this is the problem that you do think about?
Yes, yeah,
So
some application of
to extreme cases, like Lagrangian embedding?
I'm really interested in the intermediate cases here. Yeah. So a corollary to the main result, which I stated before, is that the following. So you take a closed aspherical symplectic manifold. So this means whenever you have a smooth map from the sphere S2 to M, and you look at the pullback U star omega, and you integrate it over S2, you get 0. That's what it means to be spherical. In particular, if pi 2 of x is 0, then this is satisfied. For example, you can take the torus T to N with the standard form, say, or any other form. And you take an integer k bigger than or equal to 2 and an integer L between 0 and k. Then the product x cross x sk with the product structure sigma plus 0 does not embed in a presymplectic way into x cross r2 times k minus L cross RL with the form sigma direct sum with the standard form and then direct sum with 0. So this result generalizes a result by Gromov, which says that Sk does not embed in a Lagrangian way into R2k for k bigger than or equal to 2. Any question?
So
you have the kernel of this two form is defines the distribution. You have no integrability whatsoever.
Yes, it's always integrable.
It's always integrable.
Yes,
from the
yes. By definition, if you have a presymplectic manifold, you assume that the form is closed, and that gives the integrability to distribution. Yeah. So here, the leaf through any point, the isotropic leaf is any point here across the whole Sk here. And the distribution is exactly the tangent space to the second factor here.
In this condition, on the embedding is much stronger than sending like leaf onto leaf or something like that.
No, it doesn't. So, well, if you have an embedding like this, yes, then the leaves are mapped to each other, right? But well, I mean, no, that's actually not true. That's true if you have like an open embedding, so if you have the same dimension. But I mean, if you take, for example, a manifold with the 0 form here, right? And here you take, like say S1, and here you take R2, right? So the leaf through a point here is really the full manifold, say S1. And on the right-hand side, the leaf through any point would just be that point because it's a symplectic manifold if you take R2 with the standard form, say. So leaves are somehow not mapped to leaves. Right? But it's the natural compatibility condition you would assume. Right? You have two forms and you want the second one to pull back. And it generalizes those questions which I mentioned, the Lagrangian embedding question and the symplectic embedding question. Any other question? Now,
so this is the consequence of theorem 1.
Yes.
How,
okay, how do you prove
how
it?
can best?
Okay, it's a quite immediate consequence. So, assume you had an embedding like this. Then you actually get an embedding of this product into X cross R2K, a presymplectic embedding, by composing this embedding with the standard embedding of this into X cross R2K. So we can forget about the L. The L equals 0 now. So then, once you have this embedding, the fact is that the minimal symplectic area of the embedded coisotropic submanifold. First of all, the image of this manifold here is going to be a coisotropic submanifold. That's a fact from linear algebra. Okay, and then the minimal symplectic area, which is defined to be the infimum over all those integrals, u star omega, where u is a map from the disk with boundary in one of the leaves, and you only take positive ones. This is actually infinity. So there are no such maps. All maps have zero energy, zero integral here. And therefore, whatever Hamiltonian diffeomorphism you take by my theorem, it has to have a leafwise fixed point. But on the other hand, you can completely displace any compact subset in R times in X cross R2K. You can always displace any compact subset of R2K in a Hamiltonian way. Namely, basically you write down H of QP. It's constant in time, and we define to be some constant, large constant times P. So the vector field is C times Q. It moves in Q direction, and now if you take C large, in time 1 you completely remove your compact subset from itself. If you want, you can make this a compactly supported function. You can cut it off outside a big ball. And this is a contradiction to my main result then, because it states a lower bounded number of leafwise fixed points if the Hamiltonian diffeomorphism is close enough to the identity.
So what is this precise statement? This is symplectic embedding?
A presymplectic embedding. So the condition is this condition here. And it has to be an embedding. As a matter of fact, you actually find a presymplectic immersion here, because there is a Lagrangian immersion of Sk into R2K. Well, okay, here probably there's some condition on L. Let's forget about the L. Let's do just L equals 0. Okay. So this is called the Whitney map. You can write it down easily, this immersion. It only has one double point. 2 points map to the same, like north and south pole map to the same point. Otherwise, it's actually an embedding. And also, you actually find an embedding of this into X cross R2K, say, so that the cohomology class of the this presymplectic form here, or symplectic form then, if you have L equals 0, pulls back to the cohomology class of the first one. So you don't find any easy topological restrictions in this case. Any other question? So in the remaining time, how long will that be?
15 minutes.
50? Oh, that sounds good. I would like to talk about some further research which I did, and some outlook on research I'm intending to do. So, I did some research on the Maslov map for coisotropic submanifolds. So let's explain this a bit. So here again we fix a symplectic manifold and the coisotropic submanifold of it. Now the question is whether we can replace the closeness of the map phi to the identity in the Hofer sense in theorem 1 by some monotonicity assumption on n. So this is something which people do in the case where n is half the dimension of n, in the Lagrangian case. And I'm wondering if there is a generalization of this to the new setting. And indeed there is. So there's a new definition of a Maslov map. And for this, we look at the set of all maps, continuous maps from the disk to M, which map the boundary to one of the isotropic leaves. So again, you have this picture where you have your coisotropic submanifold here, and say this is a leaf. Okay? So this is, see, here is the point x and this is the leaf. To x, and then you look at disks which have boundary in one of those leaves, but the leaf may vary. And for such maps, you can associate a real number to them, which I would call the Maslov index. So there's a natural such map. It involves a linear holonomy along a leaf. And it's a generalization of the Maslov map for in the Lagrangian case. It's also a generalization of the Chern number if you have the case where n equals n. I would like to mention that an equivalent definition of this map was given by Victor Ginzburg recently. And also Young and O defined a Maslov map for graded coisotropics and manifolds. So he imposes an additional structure on the coisotropics and manifold. And not every coisotropics and manifold is gradable, but those which are, for those who choose a grading, and then you have a map like this. Actually, he's not that restrictive with the map, with the domain. So in his case, the disk is allowed to have boundary just on n, not on a leaf. And if you actually take maps which have boundary on a leaf, then the two maps agree. Okay. Now, using this map here, we can define monotonicity of n and the minimum Maslov number of it, and then we can formulate the following theorem. Namely, whenever you have a geometrically bounded symplectic manifold and a closed, regular, and monotone quadratropics and manifold, and you assume that the pair n phi is not degenerate, then the number of leafwise fixed points is bounded below by this sum of the Betti numbers, where the index ranges over certain numbers only, and the minimum Maslov number enters here. So the proof of this result is based on a Lagrangian embedding of n and a result by Peter Albers. And as a corollary, you get again a presymplectic non-embedding result.
Could you explain more what monotone, what going by n is monotone?
Okay, so this means I haven't defined the Maslov map. That would go a bit too far. So I'm happy to do this after the talk to define the Maslov map. But monotonicity, once you know what the Maslov map is, means that there exists a positive constant C such that the first Chern number, no, not the first Chern number, Maslov number. So you n only the n, say with the disk, is a multiple of the integration map. So let me give this the name I. So I of a disk U like this is by definition the integral U star over the disk. That's what monotone means. As an example, the unit sphere inside R2n, S2n minus 1, is very well understood. So if you look at the map which maps the disk to, well, the first factor in R2, the first factor of R2 in R2n, right? So it's the inclusion map in R2, and then you cross it just with the point 0 and so on. So this map has Maslov number 2. It's like in the case where n equals 1. Then you just fill out the circle, and this map has Maslov number 2. And it's monotone. Okay? So there are a lot of examples which are actually monotone. And right. I'm happy to give you maybe a more concrete example where you can see what the theorem says, maybe after the talk, if that's fine. I would like to give you some more outlook on current research, which I'm doing. So now you can ask what happens if you have a non-regular n. So in both theorems, I assume that the coisotropics and manifold is regular, so the symplectic quotient exists. Now, in the general situation, I'm working on the third homology for the pair phi n. So the generators of this homology are by definition the leafwise fixed points. And the boundary operator is defined by this formula here. Okay, so you, well, when you apply it to a leafwise fixed point, you sum over all other leafwise fixed points, and you take a certain coefficient here. And if you're lucky, the boundary operator will square to 0, and then you get a homology. Now, the interesting question is how to define this number n of x minus x plus. So my approach is to define to be the number of all pairs uv, which are smooth maps from the strip to n cross n, satisfying the following conditions here. And then I have to divide by time shift. Whenever you have a map satisfying, well, a good equation, then you can somehow shift it in time, and I have to mod out by this. So the conditions are the following. The first map is holomorphic in the usual sense. And the second map satisfies some holomorphicity condition in the linear symplectic quotient. So when you have a coisotropic submanifold, it comes with the isotropic distribution, and if you quotient out the tangent bundle to the coisotropic submanifold by this distribution, you get the linear symplectic quotient bundle over the manifold n. And there is some sense in writing down the Cauchy-Riemann equation here, using this quotient. And then you also need some gauge fixing condition. So here H is a horizontal distribution on n. It's orthogonal, not orthogonal, it's complementary to the isotropic distribution. So the isotropic distribution, remember, is the tangent distribution to the leaves here. Okay, so you take some complement of it, H, and then this PRH is the projection along this H onto the isotropic distribution. And then you can write down a second order differential equation like this. It's a bit like Laplace equation. Right? And this I would call a gauge fixing condition for V. Right? So the idea is somehow that V should be a map to the symplectic quotient, but the symplectic quotient is not well defined now. So we actually lift it to map to n. But then we need some gauge fixing, because when we lift the map from the quotient to upstairs, we have a lot of freedom. Right? We can move it in a leaf at each point. So that's a gauge fixing condition here. And then I have some asymptotic conditions involving the 2 points x minus and x plus, leave as fixed points here. And finally, I want to have some boundary conditions involving the leaf relation. So this Rn omega is the set of all pairs in n cross n, which are on the same leaf. And it so should have finite energy, the pair uv and Maslov index 1. So here you need another definition of a Maslov index. It's not exactly the one I talked about before, because here you have strips, and this should always be an integer, this Maslov index here.
So there you have, go back, layer homology. CF is the summation of all Z2 X.
Yes.
What is that? This is just a copy of Z2.
Yes, a copy of Z2 numbers labeled by X.
X,
yeah,
okay.
Right. It's a formal way of writing a copy of Z2. Now, I would like to mention that this is the interesting part of the conditions here. And this has been studied by Hofer, Wysotsky, Zehner in a different context. So they looked at a contact manifold and its symplectization, and then they wrote down this equation here, and they used it to for finding closed wave orbits. So, the idea is to use it for a proof of the Weinstein conjecture. So it has been studied before, this equation. Now, is there any other question?
So which part is more for this?
Well, making this map well-defined. Whenever you want to define something in symplectic topology, meaning symplectic topology means you have some sort of Cauchy-Riemann equation. That's my understanding of it. Then you have to actually come up with a setting where you look at the Banach manifold of all maps, and then you have a Fredholm section of some Banach bundle or maybe Hilbert bundle over it, and this involves analysis. I think the main difficulty here is, the analysis for the Lagrangian case has been worked out, and basically this is the same thing, except that there is no real symplectic quotient. So the main difficulty, I think, is bubbling. So what I'm really working on right now is I want to prove some inequality for the energy density of UV. So here I mean the energy density which does not see the direction in the isotropic direction. It's somehow, you can write down an energy density in the quotient if you want, right? And then I want to prove an inequality like this. And once you have this, then there is quantization of energy. And once you have quantization of energy, I think the theory should work out the way it did before the Lagrangian case, using this Lagrangian embedding of n, which I didn't really explain here. Any other question?
I was lost, but is it a Pn? What is a presymplectic or what is this?
So
We are working on
n is a Coisotropic submanifold of a given symplectic manifold M omega. And phi is a Hamiltonian diffeomorphism on M, so it's a map from M to M. Any other question?
so Flare
yeah.
homology in the
usual case.
how different are they?
Okay, so what I'm saying here is going to be some sort of Lagrangian Flare homology for this construction.
So the usual is your Lagrangian.
Yes. So when you do Lagrangian Flare homology, what you start with is a Lagrangian submanifold n in M, and you take a Hamiltonian diffeomorphism of this of M, and you look at the Lagrangian submanifold. Say it's the circle inside R2, right? I mean, and then you look at its translate under phi, and they intersect in some way, and what you count. Well, you look at the intersection points and you count holomorphic maps, holomorphic strips, which have Lagrangian boundary conditions like this, and asymptotic conditions. So under some conditions, this homology is well defined. For example, if you take T star of some closed manifold, then it's well defined. And then you can actually prove that under, if the Lagrangian, say if you take the zero section, and if you assume that the zero section intersects phi of L in a transverse way, then you can prove that the number of the Flare homology has actually rank at least the sum of the Bethe numbers of L with Z2 coefficients. So for example, if you take the units, the S1, and then you do the cotangent boundary, you get a cylinder. Now if you move this circle here in a Hamiltonian way, what happens is that whenever you move it down at some point, you have to move it up on the other side. So the total area here is going to be 0. So therefore you have 2 intersection points at least. So here you can see in an easy way that you have some intersection points. And so the intersection points here translate to leafwise intersection points, or leafwise fixed points. So maybe I can give you more details about the construction which I use here. I didn't really make it explicit. And then how this translates to Lagrangian case. So let me end with some further applications and an open question at the end. So, using my leafwise fixed point result, you can prove that there exist exotic symplectic structures on certain products of manifolds. And you can also prove lower bounds on the relative Hofer diameters. So the absolute Hofer diameter has always been proven to be infinite in all cases, which were known. I mean, it's not generally proven, but in all known cases it's proven to be infinite, but the relative one is not. There are examples, like if you take the unit ball inside R2n, it's finite. And, now using Coisotropic submanifolds, you get some lower bounds for products, and then also you can construct a capacity, symplectic capacity, using the minimal symplectic area of a Coisotropic submanifold, and you vary over all Coisotropic submanifolds. Now, this is I have some joint work here with Jan Svoboda and Juan about these, at least the first two things. Also, I would like now to end with a simple question, I think. Namely, if you have a Coisotropic submanifold n in a symplectic manifold, and you already know that it's not displaceable in a Hamiltonian way, you can wonder whether you can still displace it in a leafwise way. So you don't have leafwise fixed points. Right? So whenever you have a leafwise fixed point, of course you have an intersection point of n and phi of n, but not the other way around. Right? For example, let's take any number n bigger than or equal to 2 and a radius r which is close to 1 but bigger than 1. And you take the symplectic manifold, the ball with radius r inside R2n and the standard form, and you take the unit sphere inside R2n as Coisotropic submanifold of this, then I don't know the answer. So I talked to a few people and nobody was able to give me an answer to the question about. maybe some of the audience is able. I would be very eager to know, because it has some application on this question here. So, excuse me, please.
The manifold, the model seems to be
Yes,
simple,
yes.
but
Let's take n equals 2, even then I don't know the answer. So you look at the unit, no, the ball of radius r inside R4, and you take the unit sphere in R4, S3, and can you now leafwise displace this inside this ball of radius r, if r is small? Of course, if r is bigger than or equal to, I don't know, 3 or so, then yes, you can. But if it's small, close to 1, then I don't know. I would really like to know. So thank you very much for your attention.
do you have any further questions?